morning, everyone. Thank you for the introduction, and thank you to the organisers of the Climate Investor Forum for the opportunity to be speaking here today. I'd like to start by acknowledging and paying my respect to the Wurundjeri people of the Kulin Nation, on whose traditional lands we meet today, and extend this to all First Nations Australians whose cultures, connecting people, country and ancestors have protected the lands for thousands of years and continues to do so. As Matt said, I'm Vanessa Vongsuthi. I'm one of the research founders and head of protein engineering at Samsara Eco. And today I'm very excited to be sharing with you all our mission to deliver climate repair through infinite plastic recycling. The world produces over 400 million tonnes of plastics from fossil fuels every year. Now, my back of the napkin maths tells me that even when it's densely compacted, this is enough plastic to fill the entire MCG over 180 times. What's even more staggering is that all of this plastic contributes to over 3.4% of greenhouse gas emissions throughout its life cycle. And if we don't act on this, these emissions are projected to more than double in the next 40 years. Only 9% of all plastic produced gets recycled. And while plastics are ubiquitous across many industries, including textiles, packaging, construction, and automotive, the vast majority of what can currently be recycled commercially is clean and usually clear packaging. When this small fraction of our waste makes it to a mechanical recycling facility, if the waste stream is pure enough, it gets melted and reformed into recycled plastic. But with each cycle of this process, the plastic loses some of its quality and structural integrity, and then it must be spiked with virgin plastic to maintain usability, or it eventually meets the same fate as the rest of our plastic waste. In the face of a warming and polluted planet, governments have introduced new legislations, and the world's largest plastic producers have made global commitments towards reducing virgin plastic production. But existing recycling technology will not allow us to meet the incoming demand for high-quality recycled plastic, and it will not allow us to decouple plastics from fossil fuels. To resolve this, plastic recycling must be made tolerant to contaminations and dyes, able to handle mixed plastics and textiles, and importantly, we must be able to recycle any given plastic over and over again. It must be infinite. At Samsara Eco, we're achieving this by engineering plastic degrading enzymes, like the molecule shown here, that can rapidly break down plastics all the way to the chemical building blocks that they're made of. And our process takes place not in the hundreds of years that the natural degradation of plastic can take, but in seconds or minutes. Here's how it works. We take your biscuit trays, fast fashion clothing items, and colored bottles, and using our patented enzymatic process, we convert them into their constituent chemicals known as monomers. These monomers can then be used to make virgin quality plastic again, with no compromise to the quality of the plastic over an infinite number of cycles. As we expand on our library of enzymes, we can even upcycle these monomers derived from waste plastic into more valuable commodity chemicals. Our process provides technological advantage at each step from plastic to monomer. Firstly, we can take the feedstock that other recyclers don't want, starting with our first waste target, PET. As our process can tolerate contaminants, dyes, mixed plastics, and textiles, we divert our feedstocks from landfill, reducing the cost of our inputs. Secondly, unlike existing enzymatic recycling technology that works in batches and consumes the enzyme with each cycle, our process is continuous and reuses the enzyme over multiple cycles, reducing our conversion costs and maximizing efficiency. Thirdly, our product is equivalent to virgin plastic, providing us with a high offtake revenue. Importantly, our enzymes work in mild conditions, and our process has no energy-intensive pre-processing steps, such as thermal extrusion or cryogenic milling of the plastic, minimizing our carbon footprint to within range of current mechanical recycling. And this is crucial because the conversation around circularizing the plastic economy has shifted. It's no longer about just getting from plastic to monomers and maximizing profit. It's about how we do both of these things in a way that reduces our climate change impacts compared to virgin plastic production, and how we do this in a way that prevents further harm to the planet. The environmental benefit of the process we have developed is twofold. To quantify it, our 2030 ambition is to recycle 1.5 million tonnes of plastic per year, diverting this plastic from landfill and the natural environment, and preventing the impacts of plastic pollution and mismanaged waste. In turn, we displace the production of this plastic from fossil fuels, preventing an estimated 1.4 million tonnes of greenhouse gas emissions annually. Now, this is just for PET, but as we expand our technology to other plastics that have far worse carbon emissions associated with their virgin production, such as nylon, our potential to mitigate emissions from the plastics industry only increases. As we stand with a handful of enzymes that target two of the most commonly used plastics, PET and nylon, the total addressable market is an estimated $235 billion. However, we're building our library of enzymes to break down almost any plastic and are developing our upcycling program to rapidly diversify into other markets. Over the last 18 months, we've raced towards unlocking our goal of making plastic infinitely recyclable at scale. Our technology is proven at a lab and pilot plant scale, and we're currently performing trials with the largest consumer goods companies in the textiles and packaging industries. In parallel, we've raised $56 million in our Series A from the world's leading investors to build our first commercial facility here in Victoria. This facility will have a 20,000 tonne capacity and serve as a blueprint for future facilities with the capacity to recycle hundreds of thousands of tonnes of plastics each year. Leveraging our partnerships with the Australian National University, Main Sequence Ventures and Woolworths, our experienced team of scientists, engineers and business people are bringing infinite plastic recycling to the world. In order to succeed quickly, we are looking for feedstock and offtake partners, as well as partners to help us accelerate the build of our commercial facilities. In addition to this, we're of course looking for investment as part of our Series B raise, which will support our international expansion and growth into new markets. Of course, we're always seeking talent as well across all areas of our business, including science, technology, and strategy. In fact, here with me at the forum today are two of my colleagues, Angie Oyoung and Greg Bland from Samsara's business development team, so please keep an eye out for them. And if anything I've shared with you today excites you, come and chat to us. We would love to connect with anyone here who's interested in joining our mission, learning more about infinite plastic recycling, or simply shares our vision. And at Samsara, that vision is to build a world that never needs to make plastics or chemicals from fossil fuels again. It is deeply ambitious, but necessary. So if there's one thing that you take away from this, it's that all of the plastic we'll ever need has already been produced. With infinite plastic recycling, we can view waste as a valuable resource and put a full stop to the production of virgin plastic from fossil fuels. Thank you.
All right, we have some time for questions. I don't think we need... we do have a mic at the back there. Fantastic. So chuck up your hand. I think one at the front there and one over there and then one at the back. There you go. 3 questions already.
Thank you. It's a very impressive technology you're putting together. What's the life cycle of the enzymes that you are using to break down plastic? And where are you sourcing the enzymes from?
Yeah, it's a great question. The life cycle of the enzymes, so I guess first of all where they come from, we produce them through fermentation, as most industrial process using any enzymes or proteins would. and they last up to 7 days in our process. And we estimate through our modelling that this is enough to reduce our enzyme costs to less than 10% of that of our nearest enzymatic recycling competitors. And that's just because we can reuse those enzymes for multiple cycles of our recycling process. So we're not replenishing enzyme in every single batch of depolymerization.
I saw another one in this, yep.
Hello, Anna Freeman from the Clean Energy Council. I'm asking this in a personal capacity, but I love the way you finished that presentation by saying, if anything that I've just said has interested you, so how could every government in Australia, if not the world, be jumping up and down about this? So first of all, how is this? How unique is this? And I presume it's patented and so then the question is scale, and how can you build scale quickly enough? One last more technical question, I don't know if you answered this, but can you also use bioplastics as part of this, because they're becoming more common within the waste streams as well?
Thank you for the questions. I'll start with the first one, which is how unique is it? Obviously, there are a number of competing technologies working on advanced recycling, which I think is necessary because the problem is astronomical. In terms of enzymatic recycling, we are the first to have developed a continuous enzymatic recycling process. And so that is our main innovation, which I think provides us with the largest competitive advantage in terms of our conversion costs to get from waste plastic back to plastic again. The second question was the question of scale. So as I showed on the slide, our technology is proven at a lab and pilot plant scale, and the next stage for us is scaling to our R&D facility, which will have the capacity to recycle a few thousand tons of plastics per year. Scaling for us on the technology side, we don't envision being that large of a challenge because we don't use bespoke equipment. A lot of what we use in our process you consider as off-the-shelf industrial processing equipment, and all of the smarts lie in the engineering of the enzyme itself. And then the third part of the question was bioplastics. Yes, thank you. So bioplastics, I think, represent a really important part of solving the plastic pollution problem, which is product redesign. At the moment, they represent only about 2% of the total plastics market, and they're only recyclable in a very specific set of composting conditions. And so we are indeed expanding our technology to look at how we can apply enzymes to process corn-based plastic, for example. And so we expect, as part of our growth and part of our next Series B and growth into new markets, part of that will be looking at processing of bio-based plastics as well. Yeah.
Just one more quick question. I think there was one over there that we had. Yeah, just very quickly.
Hi, Vanessa. Jody York, Kalara Capital. Thank you. Fantastic, very compelling presentation. I'd love to say that I was coming to you with a smart science question, but you said something that I found quite compelling, which is, of course, that all of the plastic we will ever need has probably already been made, and it is already out there in the environment. Now, a lot of the, as I understand it, a lot of the plastics that end up in the ocean by volume are actually discarded fishing gear, and I think nylon's a big piece of that. Like, do you see a future path where waste that's recovered from the environment actually can be reprocessed, or is that just too dirty and messy?
Well, first of all, fishing gear, I think predominantly is nylon, which is one of the plastics that we've expanded our technology to. It's a very difficult question, but I think with infinite plastic recycling technology, how we play into that is that we would incentivize the collection of that waste, or incentivize the extended producer responsibilities associated with those products, and then hope to clean up the environment that way with our technology. Yeah.
And applause for Vanessa.